Okay, so welcome to the modern physics. If you didn't check the instructor in the last 1 hour, you were probably hoping to see somebody else. But we had to make a last-minute change in your instructor, so I will be teaching you in the semester, probably for the rest of the semester. And, well, since it has been a last-minute change, I cannot claim that I have been prepared for this course, but probably we will not have too much a problem. I don't yet have a written syllabus, but I'm hoping to prepare the syllabus within a week, so you will have the syllabus, you will know the regulations, how we will be using what we'll be doing during the lectures. And well, I will be using the projector. I will be writing on my computer, and all the lecture slides, I will just distribute it to you. I am also recording the screen capture and my sound, so I will also, those will also be available hopefully on the day of the lectures. I will upload the links in OTTO class. I will be using OTTO class. And so if you want to review the lecture, well, this is not an excuse for you not to attend the lecture, but hopefully if you miss, let's say, one lecture, you can review it later on. Now, the attendance, I don't like taking the attendance, but if I don't take the attendance, somehow just the students just disappear. So at least in the first year, you haven't. When I was teaching first-year students, what I used to do is I would just do some pop quizzes, unannounced quizzes at random times, random dates, and indirectly take the attendance like that. So as I said, I didn't yet decide whether to do the quizzes or not, but hopefully within a week, I will just let you know. As I said, I will be using the OTTO class. All the materials will be available in OTTO class. Did you use the OTTO class before? So you are already familiar with the system. As I said, I will already upload the videos, the lecture notes. Any homework that I will assign, they will also be in OTTO class. Any questions? Well, we will have 2 midterms, 1 final. The dates, I don't really know yet. Hopefully, after 5 weeks, the first midterm, around 5 weeks later, the second midterm, and then we will have the final. Now, we can decide on the date probably next week, on Monday, on our first lecture next week. Any questions? You don't like Pfizer? No, I mean, I'm not so fond of Pfizer, but I think I will, at least this semester, I will stick to it. Now, I was informed that at least for the last couple of semesters, Pfizer was also used. So if you are taking this course the second or the third time, you probably already have Pfizer. So I will not change it. I was suggested to use Crane. I mean, when I prepare the syllabus, I will have some additional textbook material and additional sources that you can use. So Crane will be in that list. Other questions? And one more thing, I always suggest my students to watch this video. Well, he's a physicist in Harvard, a condensed matter physicist, and he's also interested in physics education. So he's also doing research on physics education. So for me, this video was quite illuminating. The basic lesson of the video, if I would summarize it in a single word, is that if you don't participate, we are just wasting time here. You will not learn from me. I will be just speaking for 4 hours a week. You will be sitting there for 4 hours a week, and you will not be learning much. So it's crucial that you participate, you interrupt me whenever you like, you ask questions. Okay, when I was teaching the first-year students, again, it was also such a big classroom. One advantage of big classrooms is that there is always at least 1 or 2 students who ask so-called stupid questions. And then what happens is all the rest of the classroom learns from those stupid questions. So just ask stupid questions so that you will all learn. They are usually the greatest questions that are asked during the class. That's the problem. My voice tends to go down, so just warn me if you cannot hear me. I will try to speak up, but as I said, I just forget and my sound just goes down. Whenever you have difficulty hearing me, just warn me to speak up. So what do you expect from this course? Nothing? Did you look at least the catalog to see what is the content of this book, of this course? No comments? Well, these are the two main topics of this course. Well, these are, in fact, you can call them two most recent scientific revolutions we had. So they completely changed the way we understand how nature works, what are the fundamental principles of the nature. For example, last year you studied Newton's dynamics, and these two new concepts, they basically, one thing, they arise from the failures of Newton's classical physics, the Newton's dynamics, and also, well, the Newton's dynamics and classical electromagnetic theory were not compatible with each other. So we will also discuss that. They just don't agree with each other. So trying to combine them, we discovered relativity, and then trying to explain some observations, we discovered quantum physics. So in a sense, these are the two pillars of the modern physics and the modern technology. All the current technology is based on especially the quantum physics. So we will just make an introduction. What was the experimental failures we had? What was the experiments that we couldn't explain with classical physics, which led us to these new concepts? And as I said, these are, for example, relativity just modified drastically our understanding of time and space. Whereas the quantum physics just drastically changed what we understand from a particle. It just told us that, well, relativity told us that absolute time and absolute space doesn't exist. And quantum physics told us that there's no distinction between particles and waves. They are basically the same thing. And well, if you again remember your 109 courses, you were dealing with point particles. It just doesn't hold anymore. Well, of course, approximately, you see, sometimes the students ask, we know that Newton's mechanics is wrong, the relativity is the correct theory, so why do we study Newton's dynamics? Or the same thing, we know that classical physics is wrong because there is quantum physics, but why do we learn still classical physics? But you see, these relativity and quantum physics didn't really tell us that Newton's dynamics and classical physics were wrong. They just told us that they are limited. For example, if you want to send a space shuttle to moon, you don't need quantum physics, well, besides the technology that you are used, or you don't need relativity. If you want to use GPS, you need relativity, by the way. In fact, not just the special theory of relativity. Now, in this course, we will study the special theory of relativity, but if you want to use GPS, you need to know the general theory of relativity. Otherwise, the positions that your GPS device shows is several kilometers off. So, okay, let's start with relativity. Okay, in 110, in electromagnetic theory in first year, what was the last topic you have studied? Okay, you wrote the Maxwell's equation. Did you study electromagnetic waves? At least made a... No? Okay, you see, one prediction of Maxwell's theories was that the speed of light is equal to 1 over square root of mu 0 epsilon 0, which we denote by C. So do you see any problem with this comment?
It is not relative to when can you handle the light is traveling in wind or air?
In vacuum. This is in vacuum.
It's not relative, it's a constant.
It's a constant. But you see, in mechanics, you already learned that the speed should be relative. Well, that is called Galilean relativity, by the way. Now, what does Galilean relativity tell us? Well, you have two reference frames. Well, for the time being, at least, I will define what we mean by a reference frame, but for the time being, just assume two different coordinate axes. So we have these two coordinate axes. Let's call them O and O prime. And there is a point over there. Let's say this is the x-axis, this is the y-axis, this is the x prime axis, this is the y prime axis. Now, if I ask you what is the position of this point P relative to somebody at rest in the O prime reference frame, you can just imagine, I'm standing here, you are at this point and moving. So this point is also moving. At a given time, they are located like this. And if I ask you for the position of this point P observed by you, your friend is moving, so he will just take his ruler, make a measurement of this length, and he will determine this point to be at a distance x prime from where he is. And, well, let me just stick with the x coordinates only. So your friend is moving, he takes a ruler, this is the point P, he draws this perpendicular, and then measures this distance by his ruler. So this is this length x prime is what we call the x coordinate of that point. And then I am looking at your friend, I also see that point P. So what I do is I look at I can also measure the x-coordinate of that point. I basically do the same thing. I take that point, draw a perpendicular to my x-axis, measure its coordinate, this length. I measure this length and then say that, okay, in my reference, in the reference frame with the origin here, that point has the x-coordinate x. And I also look at your friend. Your friend was moving, but at this instant, I ask what is his x coordinate. So what you do is, your friend is over here. You draw this perpendicular line and measure this distance. And let me call it capital X. And then you say, okay, this distance is capital X. This distance is this distance between the point O prime and the point X was already measured to be x prime. So this whole distance, which is x, should be equal to capital X plus x prime. I just sum these two lengths, and I obtain the full length. Okay, so everything is moving. Your friend is moving. That point P might be moving. So if you just look at it, follow this particle for a given time, its position, x coordinate will change, let's say, by delta x. And your friend will move by delta capital X. And the position, x coordinate of the particle measured by your friend will also change by, let's say, delta x prime. So if all these changes happen in a time delta t, let me just divide by delta t. What we obtain is this delta x by delta t. Let me call it v. Well, we look at that point over there. There's a point just moving around. I look at it, its x coordinate changes by delta x in a time delta t. So I just calculate its speed to be v, its velocity to be v, the x component of the velocity. Then I look at your friend. Your friend is also moving around. So he has changed, his position has changed by delta x in a time delta t. So delta x by delta t is nothing but the velocity of your friend. And then your friend is also looking at that point moving around. And he measures the change in its position to be delta x prime in a time delta t. So this is the velocity measured by your friend. Let me just call it v prime. Now, all of this is Galilean relativity. So what Galilean relativity tells us is that if we have two reference frames or two coordinates that has some velocity relative to each other. So in this example, I was treating myself to be fixed and your friend has a velocity. And there is another point moving around. That point has different velocities according to each one of us. So he will measure some different velocity, I will measure some different velocity. And in particular, if that point and your friend are moving at the same velocities, your friend will just say that it is at rest. This much should already be familiar from 109. Now here we come to the problem. The speed of light is c for everyone. That is what Maxwell's theory predicts. Well, in fact, people didn't want to believe it first, because you have a theory, you have the equations, you have Maxwell's equations, which predicts that the speed of light should be c. Then people were asking, okay, c relative to whom? Relative to which observer? And at first, what people said was, okay, it is c relative to what we call ether. Well, what they claimed was, I mean, if you consider all the other waves you know, what other waves do you know? Do you know? Okay, there's the electromagnetic. You know the sound waves. Okay, water waves. You have the sound waves, you have the water waves. You can create waves on the string. If any one of you is playing an instrument, most of the instruments are just vibrating objects, either strings or surfaces. They all create waves. And then all of these waves has one thing in common, except an electromagnetic waves. They have a medium. There's something that vibrates, and it exists even if there is no wave. You see, a string exists, whether you create a wave on it or not. Or the same thing, air exists, whether there's sound or not, except in electromagnetic waves. So people were asking, okay, so probably it's also true for electromagnetic waves. So what is the medium that is vibrating in this and creating this electromagnetic wave? And the answer they gave was, okay, ether. There is this thing called ether. There should be this thing called ether. And its vibrations are what is creating the electromagnetic wave. So that was the hypothesis. And of course, it has to be tested. Now, how do we test such a hypothesis? Great. So the idea is this, well, this one. It's just like you probably have solved problems of people swimming across rivers, right? So the typical question is, if you have a river and the river is flowing with a velocity v, there is a swimmer over here. The swimmer can move up and down, or it can move horizontally. And even if it covers the same different distance, to the left and right or up and down. And he swims with the same speed relative to the water. It will take him different times to swim vertically to the flow or horizontally in the same direction of the flow. So it's the average time, the time it takes will be different. So if there is this thing called ether, electromagnetic waves exist everywhere. So it is the Earth should be moving along ether, but the speed of Earth is one thing is okay, if you put some device, the Michelson-Morley interferometer was basically such a mirror system. So what you do is you send some light. There is a splitter over here. What the splitter does is it just reflects some of the wave, but transmits the remaining wave. It just splits it into two. And the light goes up, then down, and it just goes left and then right. And when they meet over here, it can cross. Some of it will be reflected. So you will have what is called an interference pattern. So this was the idea. Well, one thing is Earth is moving. And even if the Earth is at rest relative to ether at this moment, the Earth is making a circular motion. It won't be at rest relative to ether at a different time. So definitely if you make this measurement for some period of time, during some periods, the Earth will be moving, the Earth and hence your experimental setup will be moving relative to Earth. And depending on in which direction your setup will be moving relative to ether, well, either it can take a longer time to go up and down than horizontally, or it can take a longer time to go horizontally than vertically, etc. But at the end of the day, if there is ether, if Earth is moving relative to this ether, the times the light ray takes to go up and down or left and right will be different. If there is such a time difference, the interference pattern changes. So that was the basic idea.
Why do you think that Earth should interfere with ether?
Well, Earth doesn't interfere with ether. You see, the concept of ether is something that fills the universe, like the air over here. Because everywhere in the universe, there's electromagnetic waves, as far as we know. So if the medium of electromagnetic waves is ether, that means ether is filling everywhere. Earth is inside the ether. So as Earth is moving in the universe around the sun, it should be moving inside the ether.
Did we repeat these experiments in other orientations?
Yes, because you see, this, as your friend points out, great comment. You see, here, this argument works only if the speed of ether is not along this line. Because if the speed of ether is at 45 degrees, the effect on this arm will be exactly the same as the effect on this arm. So there won't be any change due to the motion of the ether. So this is a rotating platform, so you can rotate it. And the result was that nothing. There was no change in the interference as you rotate your platform. Because as you rotate your platform, the speed of the different arms relative to ether will be changing, and hence you expect changes in the interference pattern. But it never arises. They never observed it. And kind of experimentally verifying that, well, there are some loopholes, that the speed of light is constant. Well, are there any loopholes? Yes, I mean, when people first made the Michelson-Morley experiment was first announced, I mean, there were all alternative models. Basically, this assumes that ether is not, my argument here assumes that ether is not moving with Earth. So it might be that maybe there is an ether around Earth that is moving with us, so that the Earth doesn't move relative to the ether very close to the Earth. In that case, again, we will not observe this change in the interference phenomenon. But then,
But when we rotate the interference
Imagine this one. There is a similar analogy to imagine you are moving in a bus. Okay? Inside, you make some sound. You have probably heard of Doppler effect, right? So you know that if somebody is moving relative to you and makes some sound, like if you have heard of the ambulance, that's the typical example, when it is coming towards you, the sound is different than when it's moving away from you. And but it doesn't happen if everything is moving with the medium. I mean, let's assume you are in the bus, you make some sound. Even if the bus or the plane, let's say, is moving faster than the speed of light, the sound is moving with the plane inside because the medium is moving with the plane. You see, if something is moving faster than the speed of light, let's say I'm moving in this direction faster than the speed of sound, and you shout at me, I will not hear you. But if we are both in if I am also carrying my medium with me, I will eventually hear you. Here you can claim that there's a similar thing happens. The Earth might be moving a region of ether with it. So if this is the case, then the Earth is not moving relative to ether. So you won't be able to observe the changes in the velocity of ether relative to these arms. Basically, there's no relative velocity. The Earth is at rest.
So what if we constantly rotate the system constantly
Okay.
around itself and around the center? So wouldn't it make a change? And
Sure.
If the ether is moving same as Earth, rotating the system would close the loophole, I think.
Yeah, I mean, of course now, it's very difficult in physics to close any loopholes. But I mean, you can always come up with fine-tuning, some fine modifications of your model, which can still create some loopholes. But at the end of the day, using arguments like yours, I mean, if we want to stick with the idea of ether, we had to make a very complicated model of ether. And another thing we like in science is that usually simpler models has more truth in them than more complicated models. So at the end of the day, we gave up on the idea of ether. Of course, this had drastic consequences. Like, okay, if there's no ether, how do we explain this? How do we explain that every observer sees the speed of light the same? Let's just imagine the speed of light c is 3 times 10 to the power 8. Meters per second. Now let me just imagine this one. Suppose there's an observer over here. O. And there's another observer, O prime. And let's assume that this O prime is moving with a speed relative to O, measured by O, by 2.9 times 10 to the power 8 meters per second. And let's say that the O waits 1 second. So at t equal to 0, the O prime just turns on a flashlight. Now let me just assume this to be 3 times 10 to the power 8 minus 1 meters per second. It's very close to the speed of light. At t equal to 0, the observer O, let's say I'm the observer. You are moving at that speed. I measure your speed to be that much. So at some time, you just turn on a flashlight. And I wait just for 1 second. After 1 second, observed by O, well, the flashlight had moved 3 times 10 to the power 8 meters per second times 1 second. That is how much light has moved. Again, these measurements, I'm making these measurements. And you have moved by 3 times 10 to the power 8 meters per second minus 1 meters per second times 1 second. Again, I'm making the measurements. Because in this special theory of relativity, the thing that gets the most confusing is who is measuring which quantity. So that's why I'm constantly stressing that, at least in these things, I am the one making the measurement. And, well, you just cancel them. This is just 1 meters. So when I look at the light ray that your friend has created by the flashlight, I see that the light ray, the beginning of the light ray, is just 1 meters ahead of your friend after 1 second. But still, your friend should measure the speed of light to be 3 times 10 to the power 8 meters per second. You see, if he just waits 1 second, he should see the light ray to be at a distance 3 times 10 to the power 8 meters per second. But when I wait 1 second, I just see it 1 meters per second. So that's kind of the problem. How can we explain this thing? Now, let me go back in this Galilean relativity. We made several assumptions over here. Can you pinpoint the assumptions we made in this derivation? Well, something should be wrong with this derivation. Otherwise, different observers should measure different speeds. But they don't. Something is wrong. Some of our assumptions when we are writing those equations should be wrong. What are the assumptions?
Time is absolute.
What do you mean by time is absolute? Okay, that was one assumption. You see, if you look at this quantity over here, I said that this quantity is equal to the v prime, which is the speed measured by him. But the speed measured by him should be the distance covered by the object measured by him divided by the time it took measured by him. This delta t over here is the time that I measured. The time difference that I measured need not be equal to the time difference that he measured. So that is one problem. So actually this should be delta t prime. Okay, there is one more assumption I made.
Distances are absolute.
Which means?
When I measure 1 meter in one place or in one time, then it means my friend will exactly measure it in some other time and some other time.
Okay, what is wrong in this equation then? Okay, we already said delta t's are wrong. But even without the delta t's, you see we have the delta x is equal to delta capital X plus delta x prime.
Maybe explain the correction so that it will be one, will be a fewer.
No, I mean, none of these are corrections. The delta over there just means it's the change in some time. But when I'm writing that equality, I'm making a mistake. You are on the right track. What is the mistake I'm making here?
We can't just sum them up.
We cannot. You see, if you look at over here, the assumption I made was this distance measured by him should be equal to this distance measured by me. This need not be correct. And in fact, it turns out to be false. Let me call this x double prime. X double prime is not equal to x prime. You see, basically, I'm looking at these 2 points. He looks at those 2 points, makes a length measurement. He will find some length. And then I look at the same distance. I make a measurement of the same length. And I'm assuming that I will be measuring the same length. That was the second assumption I made. Basically, I have these two assumptions. One, the length measurements should be the same. That is what I assume, or what Galileo had assumed. Second, the time differences between, let's say, two events should be the same. Those assumptions turned out to be wrong. Now, of course, we need to correct them. Just claiming that they are wrong doesn't help us much good. We have to find the correct relationships between those. So let's start with time dilation. Well, before going to time dilation, let me define the reference frames. I will be using reference frames quite frequently. What we mean by a reference frame, or what we mean by an event. Now, what we mean by an event in physics is a position and a time. So when you, for example, when there is a, when there is a concert, what you say, the concert will be here at this time. So that's an event. So this kind of, for us, the important thing would be, where will it be and when does it happen? And the reference frames are just constructs that allow us to measure the position of objects and the time of the events. Position and time of the events. So we can just imagine when we are actually choosing a reference frame, or let's say a coordinate axis, we are choosing some origin. That's one thing we choose. We are choosing some direction for our axes. Well, I'm not plotting the third one, but there's also the third axis. And then what we do is we just imagine some kind of a grid, horizontal and vertical lines. So we just imagine all these horizontal and vertical lines. So if an event happens at a point, then we can right away, by looking at which horizontal and which vertical line passes at that point, we can just determine the x and the y and the z coordinate of that point. So we know the position of the event. And now what we imagine is that not just the horizontal and vertical axes, we also imagine that at every point there is a clock. And the clocks are synchronized so that they all show the same time. So if an event happens here, by looking at the horizontal and vertical lines that is passing through that point, we can determine the position. And by looking at the clock that is at that position, we can determine the time of the event. Well, I will also ask the question, what does it mean? What do you mean by synchronized? We will come to that question later on, but just keep in mind, this is an assumption, well, let's say another assumption you make, assumption in quotes. In a given reference frame, at least, I know that I can synchronize clocks. I can just, let's say, pick up two clocks and go and sit in the middle. And when and we agree that when they receive some light beam, light signal, they should set these two clocks at a given time. So I sit in the middle, send the light rays in two different directions, and when they receive the light signal, they just adjust the clocks, and at that point I know that these two clocks are synchronized. So I can define what I mean by, I can synchronize my clocks in a given reference frame. And then there is another special kind of reference frame, so-called inertial reference frame. What's an inertial reference frame? Hmm? Well, essentially it's the Newton's first law. So if you can isolate an object, and if there are no forces acting on it, if it is moving, it should keep moving with the same speed. If it is at rest, it should stay at rest. If you have chosen a reference frame in which this is not satisfied, then that reference frame is not an inertial reference frame. Okay, so we had already mentioned one of the postulates of special theory of relativity, that the speed of light should be the same. The second postulate is that all physical laws should be the same. In every inertial reference frame. So these two are what leads us to will lead us to the special theory of relativity. Well, if you remove this constraint of inertial, if you say that all laws of physics should be valid in every reference frame, whether inertial or not, what you discover is general theory of relativity. And so you can understand gravity. Okay, so these are the two postulates of special theory of relativity. Now let's see what it means for time dilation. How does time change from frame to frame? Let's make a thought experiment. Okay, any questions? We don't have time for that, but if you have any questions, we can discuss, give a break, and then we have the time dilation. Okay, I cannot hear you. Well, okay, so we have 5 minutes before the break. I wouldn't like to start the discussion of time dilation because we will not finish it. But if you have any questions before the break, we can just discuss it. And then after the break, we can continue with time dilation. No? Okay, your break is still 10 minutes. We will start at 35.